Hello, I'm Pete Harris from I'm technical director for our performance tools team, but I also get involved in a lot of our frontline DevRel support. If we get developers coming and saying, "Oh, we've got a game that's not performing, or it's got crash issues, or rendering artifacts," the tools team often get involved as part of that frontline support team to help developers solve their problem and get their game shipped. So this talk's going to talk about libGPULayers, which is a new open source project. We've had tools like this internally forever. They're super useful. And we kind of felt actually it would just be easy to have these as an open source project that when we're working with a developer, they get access to the same tooling that we have. Focused on Android, I'll cover some of that a bit later. Extending it to other platforms probably isn't too hard. So in this, kind of briefly, what are layer drivers? Most people will have used Khronos validation. How many of you have ever built a layer driver, like written one? Yeah, thought that was the answer. So if you're not an IHV or you're not Linergy, the odds of you having built a layer driver by yourself is quite small, but they're actually a super powerful development tool in their own right. But they have the classic Vulkan problem of they're not a joy to use, and it's an awful lot of boilerplate code to write. So why did ARM want to go and do a new open source project called libGPULayers? What can this do? This is VK Bootstrap for layers, by the way. So thank you, Charles, for stealing the thunder on that one. And then a few thoughts of kind of when you're a layer developer, you're in a slightly weird position as far as the API is concerned. Vulkan makes opinions about things, and those opinions are fine if you're an app or a driver. But when you're a layer and you're piggy in the middle, there's some interesting quirks when it comes to writing code. And then kind of how does that manifest through the API? Okay, so layer driver essentials, right? So layers provide through the loader a standard way of stuffing code in the call path, right? That's what a layer is. And most people do this with the validation layers, but it's a general purpose tool. The loader provides an API that does this as a standard interface for how layers get injected. And this is a whole world of pain better than DLOpen, DLSim, and all the nasty stuff we had to do for Gles drivers. So thank you for Vulkan. This is the way that you should build APIs. It is a super valuable capability to have. A layer can just mess with the call chain. So obviously you can do monitoring, so don't change anything, just snoop and monitor. That's kind of your Khronos validation model. They can expose whole new functionality. The Khronos timeline SEM layer being a good example. So it's production, it's performant, you can ship it. It just gives you some new tools. And when it comes to support, we can change what the application's doing. And the application doesn't even know. And that is a very, very useful thing to have. So as an IHV, we really love layer drivers. And just because we're an IP provider, we're in a slightly weird position. We don't build the applications. Obviously, that comes from the game developer or the app developer. We get binaries. It's a great industry to work in. People are fairly open at sharing builds of things that we can go and play with. But we also don't build the production drivers. Right? We're not the platform manufacturer. So we have a driver development kit as source code that goes to our OEMs. They build the drivers for their phones. On a release build Android device, we usually can't replace the driver. So things we'd like to be able to do, hack driver, add debugging, recompile, ship it, we can't do it. We don't have all the pieces. So layers provide us with a tool that we can inject code into these systems as part of tech support, that when a vendor brings us an issue that only manifests on a particular device, and that could be driver issues, it could be hardware issues, could be things the OEM has done to those devices. It could just be timing. That's quite a common one where lots of different GPU configurations in the wild, that device happens to hit that particular timing point and sync becomes a problem. We can actually help debug on that device, even though a lot of the bits of the system software are black box for us. So why do libGPULayers? We want to be able to build quick iteration layers as part of tech support. We can get something into those platforms very quickly. My goal for a layer, I can build it in 2 minutes, right? Take a function, change some functionality. It should not be days and days of effort to go and build one of these things. So very much Charles's talk from yesterday about VK Bootstrap for applications. This is a big part of VK Bootstrap for layers, right? I want a tool that can let me build a layer that I can hit go, hit build, and get on with the day job. So we can build layers that just investigate what the application is doing. We'd normally use RenderDoc for that, but sometimes it's useful just to have a trace that we can do non-invasively. and just what functions is it calling? Is it using a particular combination of parameters? Once we've got some ideas about what's going wrong, build a layer to test a hypothesis. Once we have an idea for a fix or a workaround, build a layer to actually deploy that into the binary we have. Does the problem go away? So it's like an empirical version of validation layers, right? Validation is static analysis. Look at everything that's happening and go, no, you're wrong. This is the suck it and see approach to validation, right? Try it. Does the problem go away? It's not a guarantee that's the fix. You might just be hiding it, but usually it's a very, very strong indication you're looking in the right area. Making layers by hand is tedious. As per earlier talks, Vulkan likes typing. And for a layer, you have twice as much typing as an application. You have to talk to the driver. We have to talk to the application and the driver. So we have boilerplate on both sides. And we have to go and generate all of that. And because the call path here is entirely dynamic, it's entirely resolved by the loader using getProcedure. If it goes wrong, it often explodes in weird and wonderful ways sometime after you made the mistake. So debugging is a pain because when you connect GDB and you get a fault, it's like, this is not the bit that went wrong. It went wrong a few million cycles ago. And we found ourselves, a lot like Charles, right, starting a new project. Okay, that one kind of worked. And then we don't do one for a few months, and then we have to do a new one, and we make the same mistakes. So wouldn't it be nice if we just had some tools that would do this for us? So goal number one, let's provide some tools that can automate layer creation. Just hit go, you get a no-op layer. It doesn't do anything, but it's fully formed, it's viable. You just need to edit it to go and do your fun bit of code that you want it to do. Goal number two, we have some layers that we use. Let's give them to you guys, right? If you're seeing the same kind of problems, both for like support and tech support, we can give you a layer that can help and like get you through some of the initial triage questions we're going to ask. If you raise a support request, the first question is going to be, have you tried serializing your workloads? Have you tried sticking device weight idle after your things? Have you tried using robustness? Have you tried removing relax precision? And having to go and hack that in yourself to your application is really annoying, especially if you're under a game engine. So just have a layer that lets you go down all the options, right? Secondly, we produce performance tools. We want to inject or use layers to collect information that we can then put into our other tools and put API awareness into data visualizations. And again, we've had those as internal layers. We ship binaries. Usually we get someone going, I love this tool, but can I just have this other bit of data? And every partner we talk to, OEMs, developers, they all want something a bit different. So fine, we'll make the layer open source. There's a core piece of functionality there, but the protocol is extensible. If you want something custom, great, go add, please, right? You can do that lower latency than we can. So different types of layer. There's really two ways you can build layers. The first is a wrapping layer. You get a driver handle, which is just a pointer to a driver structure. Your layer can wrap that in a layer structure and then pass that up to the application. This is performant. When you get a handle, you can just dereference it and use it. The challenge is you have to intercept every single handle ever, because if a driver sees a layer handle, it's going to think it's a driver structure and it's going to explode. Please never build wrapping layers. Everyone's immediate thought is, I'm going to go and build a layer. I'll write it like this. It's a whole world of pain that you do not want to go down. Instead, the preferred pattern is forwarding layers. We get a driver handle to the layer. If the layer wants to allocate adjunct data, it creates a copy, and it uses the dispatchable handle for device and instance. That's the entire reason for dispatchable handles existing, is that a layer can use it as sideband information. And a buffer handle, an image handle, we can use that as a key as well. This is much easier to write. You can just peephole the few functions you want. It does make the dispatch path less efficient. You're now doing a map lookup on every function call to get the indirection. But if you want to write layers quickly, this is generally the way to do it. So our tooling is designed to help you build this kind of layer. So the first bit of tooling is VK bootstrap for layers, effectively. It's an ideal problem for automation. Mostly we're just looking at API calls, building dispatch tables, adding function prototypes, all that boring stuff. So luckily, Vulkan has a machine-readable XML spec. So great, let's auto-generate it. I've worked on lots of code interception tooling over the years, going back to OpenGL and OpenGL-ES. And an awful lot of them have fun text templating languages. So you have text templates that have conditional code generation in them, and then you use that as part of your build system to make your native code, and then you compile that into your binary, and you end up with sort of Turing complete text templates. And they're just a whole world of pain. So no text templates. That was my rule number one. We are not going down that path again. I've done it 3 times. So the goal of this was developers who create layers just write C++. They don't have to handle text templating at all. But we also want to make it easy to merge Vulkan API updates. The working group specs faster than we can generate tools. So how do we keep updating the layers with new stuff? So you're very productive working group, well done. And because we use this as tech support, they're not designed to be super fast runtime layers, right? These are prioritizing poor tech support engineer iteration time because we have a developer shouting at us saying, I can't ship my game. So how do we get that working? And we're willing to sacrifice some performance and code niceness to make things work. The way we solved this really was splitting things into 2 parts. We have a common code generator, which is the part that reads the XML spec. It's going to go and generate all your dispatch tables or your intercept tables, and a whole pile of, well, a small amount of manually authored code that's going to handle the custom things a layer has to do. VK create device, VK create instance, VK enumerate layer properties, all those kind of functions. But there's only 5 or 6 of them, so it's not too bad. There's then a tool for creating a new layer project. This will give you the other bits of code, and this is where you just drop in the bits of code that you want. And then per layer, we then compile and link those pieces together. This is mostly really, really boring code. It's just function pointers and structs and dispatch tables and mappings. There's just a lot of it. I think there's 400 and something entry points now for Vulkan with extensions. And you just don't want to write that code by hand. The only point where we hit a kind of design that's clever, it's not that complicated, is just we have generated function tables for intercepts and dispatch, but the things you want to intercept vary per layer. So we want per layer modification of what we're intercepting, but it's generated code. If you try and do this at the source level, you're going to have merge pain. So we let the linker do the heavy lifting. We're doing C++ function templates with tag dispatch. This is the only clever thing in the whole project. Everything else is just grunt work. So in the common code, we generate our dispatch table with all our function pointers that we want to go and resolve. We have an empty struct called user tag, which is just a tag type for template resolution. And the linker is going to try and look for vkfoo user tag, right? And the common code will provide a default implementation that does nothing other than just do the indirection, pass through to the driver. So it's a no-op, other than the fact it has a bit of tracing in for kind of that initial triage of which functions is it using, but it doesn't do anything itself. And then in the per layer code, you just provide the specializations for the small number of functions you actually want to go and do, and then you just let the linker do the heavy lifting for you. So we resolve the structure at link time, not at compile time. That's as complex as our C++ gets, right? Because we want to iterate fast, we provide some utilities. So that when you generate a project, you get an Android build script, which is just a wrapper around, yes, CMake, sorry, Android NDK like CMake. And a very, very basic configure script, which will push files to your Android device, configure the Android environment. It has its own loader. It's different to the Khronos loader. So set system properties. And it can optionally do useful things that we also need, like capturing logcat, capturing Perfetto traces, those kind of things. So from generating a layer, hitting build and installing it, probably takes about 30 seconds. It's a perfectly viable layer. You can build it. That default layer does nothing. It's got no functionality in it, but all the entry points are there, and it will do things. So that's there today. If you have a tool and you want to, what happens if I set this flag on images or something? It's very easy just to generate a layer, insert the one function you want to go and fiddle with, modify the parameters, and stick it on and run it. Seconds to run. That's often going to be far faster than your game engine rebuild time, right? So for simple mods, it's a great tool. As part of this, we also provide 2 standard layers as binaries, as ARM provided layers, sorry. as part of the open source project. This is going to grow. So the first version of this project was in November. We're growing it over time as we find time to productize things. The first layer is that support layer. So let's have an empirical validation layer with switches that you can turn on or off, and we can force certain interesting behaviors. And this is primarily useful for rendering artifacts, device lost errors, like RenderDoc's not great if you get a crash, for example. So how do we have some layer with a config file where you can toggle options on or off? So force serialize your queues, stuff in more conservative pipeline barriers. It's not there yet, but the wait idle patch is on a branch locally. So force wait idle after every workload. So we can modify SPIR-V. So if we think you've got a precision problem, so you've just got some floating point issues at FP16, we can just strip out relaxed precision. We can't currently rewrite explicit types, but that's on the list of things to try as well. Just a bit harder around ABI and not breaking things. We also use this for some kind of quick and dirty performance experiments. So we have, with the VKEXT compression control extension, we can turn off frame buffer compression. We can turn on lossy compression at certain bit rates. So we can force enable or disable that for compatible images. Force robustness is another thing that's not there yet, but is coming. And this is normally, say, the first set of questions we're going to go and ask a developer. Have you tried this? Have you tried this? Have you tried this? It normally narrows things down very, very quickly because not everything's a validation error, right? It's passing validation, it's just broken. So you're using the application, the API correctly, your algorithm's just broken. So this is kind of the what next. After you fix the validation errors, if you've still got problems, here are some tools that you can look at. So new project, the first version of this went live 3 weeks ago. We're adding stuff every week at the moment. So this is going to grow over time. The second tool, so my team maintains a whole pile of performance tools. One of the things is what's running on the GPU. We have an integration into Perfetto, which is the Android trace system. So it's a high performance event trace tool. So the driver has an integration with Perfetto. So we can see for the GPU queues, all the workloads that are running and they get timestamped. But what it's going to give you is Vulkan handles. Completely useless, right? If you're an application developer on top of Unity or Epic, what is handle OXF31294B? I don't know, right? And increasingly, as we move to things like dynamic rendering, render passes don't even have handles because you've lost the render pass object. It's just a dynamic thing in the command stream. So we can't even name it. So we want to have a semantic layer that can collect interesting API context and label these boxes. What are they? Hopefully in a way the application developer can recognize. So we have a layer that sits on top of our, it sits on top of the API. We can inject debug markers into the trace, which Perfetto can key on, and then we can export a metadata side channel, and then we have tools that can stitch these two things together. So for example, for one of the boxes, we can output the application debug label, we can output resolution, we can output number of draw calls per render pass, we can look at load op and store op, obviously important for a tiler. And again, this is one of those views where people want different stuff all the time. So open source the layer, people can customize it and things like that. So the viewer is open source as well. It's a bit ropey. It's a Python viewer. You get millions of objects coming in from Perfetto and the metadata trace. Python doesn't like having millions of very small objects from performance. So it can take a bit of time to chunk on loading a trace. But once it's open, it's pretty fast. This will end up as part of our Streamline profiler, but it's not there yet. Give us a few months. Not published yet, but coming is a GPU performance layer. So because we're tile-based, we're very heavily overlapping and pipelining workloads. If you want to measure per workload performance counters or per workload time, we have to serialize things. And then you can time workloads without the pipelining messing up the data. So we're going to have a layer that will do that for you, injecting barriers, injecting the counter queries wherever we can. And you'll get a kind of CSV file out for your keyframes with here's all your debug labels, here's all the things that happened, and whatnot. Our desire for this eventually is that it can do an on-screen overlay. So you just get little spark lines in the corner of your kind of key metrics. But that'll be a bit further out. So this isn't there on the open source project yet. Give me a month and it will be. So finally, just some development thoughts around where layers fit in Vulkan. They're a really weird fit to the API because Vulkan's an application API and it has opinions about what applications should and shouldn't do. And layers are built on top of an application API while pretending to be a driver. So there are just things that you want to do that Vulkan doesn't really let you do. So like, as an example, quite often like we're wrapping application behavior. And for like nice, neat, quick code, an ideal would be there's some stuff, and then as you go up the layer stack, you just bracket this in your different layers doing things. So the app does something first, then each layer does its pre-flight, we do some GPU work, going back up the stack, each layer does its cleanup, then the app cleanup happens last. This would be beautiful because we know the app can't delete something while we're still holding a reference to it. Great. Okay, we've got a queue submit, it's got a fence. Let's do something with that fence, right? I'm going to swap the fence for a layer fence. The layer's going to wait on that. Great, works. How do I signal the application fence? There is no API in Vulkan which lets a layer signal a fence. I mean, potentially you could do it with external fences that you import, but so there's some stuff that you kind of think is easy or could be easy, and then it gets exceptionally hard to build in practice. In reality, that boat's kind of sailed. Timeline sems kind of blow that one out of the water anyway. But kind of making a layer order things with the application is actually quite hard, especially on that work completion path. And I don't want to write code to virtualize the entire sync subsystem for Vulkan. So similarly, Vulkan has opinions about resource lifecycle. You know what you're doing. I don't. I just have to handle whatever the API is giving me. So what you actually end up with is going to be something much closer to this, right? We have the app fence, we can't virtualize, so that's there. We can't add a second fence, Vulkan only has one fence. So we're going to add a timeline sem for our bits. We're then going to wait on the timeline sem for our cleanup. But the challenge now is the cleanup's now racy. We have no idea which of those cleanup things is going to run first. So you end up kind of having to code a little bit defensively, decouple the layer resource from the app resource it's associated with, and then ref count the layer resources. So we're really writing a Eclairs driver, right? Fine. It works. No problem. It's just not very Vulkan-like. So if you've never written a layer before and you try and write things in a Vulkan style, there's just some interesting behaviors. Similarly, Vulkan says, you know what your workloads are. Like for tools, we generally care about your verbs, right? Your render passes, your compute dispatches, your ray trace transfers, your ray trace calls, your transfer jobs. We want to instrument your workloads. That's the verbs that are going to go and run on the GPU. And kind of original Vulkan was like, yeah, everything's in the command buffer. It's fine, right? You just record your tooling state when you record your command buffer. Over time, more and more things are kind of drifting out of the command buffer. So dynamic render passes, we mentioned yesterday in the panel session, they can split across multiple render passes. You can suspend and resume them. How many draw calls do you have? I don't know at record time, right? Until you do that at submit time, you have to go and look at all the command buffers and walk through the command stream and go, 7, adding those two numbers together or whatever. It works, but it's work. Debug markers, the stack belongs to the queue. It's not command buffer scoped, which is great, but we have to kind of virtualize that. Indirect parameters obviously resolve at runtime, cool. The design pattern we've ended up with effectively is by having software command streams. So whenever you record a command buffer, there's a pre-submit and a post-submit command stream that the layer's going to run. It's a software construct. On submit, we run through the submit time command stream. That plays into the queue where we can persist any queue level state. On cleanup, we get a second command stream. It's going to run through all the cleanup operations. Works fine, useful design pattern. That is how I'd recommend to go and do it. Finally, just some development niggles. Android has its own loader for reasons, and it's very basic. So the loader API has a v0 API, a v1 API, a v2 API, and obviously the later versions added some useful stuff. The major missing thing for the V0 API that Android uses is that there's no support for chain calling pre-instance functions. So in Charles' previous talk, there were some functions you can call before you even have an instance. So what API version are you? What instance extensions do you have? Because they are before you have an instance, you have no dispatchable handle. A layer cannot resolve its dispatch thing with the standard mechanism. So the V2 interface added a new mechanism for chain calling for instance functions, which would let us do this. Android doesn't support it. So if you layer multiple layers, you have no way of knowing what extensions are beneath you. You can't run that query. So on Android, there's a little bit of hit and hope. We're going to turn things on the assumption they're there, and it might crash. Sorry, there's no better way of doing it. It does happen to work if you're the bottom of the stack and the thing below you is the driver. But if you're 2 layers up and there's a layer below you, it can't work. So hopefully that one can get looked at some point. We want to instrument command buffers. So we inject debug labels. We really like those labels to be unique. But there's just all the kind of warts and niggles. Again, my question yesterday in the panel session, like things like multi-submit command buffers. We can't guarantee that command buffer is only submitted once. So is that label unique? Well, it may not be. Is it guaranteed to be the same workload, just repeated? Well, not if it's indirect. The parameters can change. Most tools ignore this as a warning. Because it's hugely complicated to support properly and it adds overhead in the common case, and no apps really do this. I think we fixed the tutorials now that we don't use these. So just be aware of the fact there's bits of Vulkan that if you try and use it with a tool, things start dropping off if it's a warty corner case. This is one example, but it's not the only one. Finally, we want to do things where not everything we want to do exists in the command stream. So we have a command buffer with lots of workloads in, and we want to inject some tooling around the workload. That could be performance counters, it could be debugging, it could be talking to some harbor registers so our tool can go and collect some data about what crashed. Those kind of things. And Vulkan says you can't do this, right? That you're not supposed to track back to the CPU mid-submit, right? It's supposed to go and complete. And for an application API, that makes perfect sense. As a tooling debug API, it makes a little bit less sense. So the right way to do this is to split the command buffer. So you have one workload per command buffer. But there's no full state inheritance in Vulkan, so you have to replay all of your commands into the previous command buffers. How many do you need to record the state? Don't know. So the answer is yes. So your runtime layer is having to deep copy all of your state setters, all of the pnext chains, just in case it has to split a command buffer and replay it later. Hands up if you want to write and maintain that code. I don't. So we cheated. Currently, and this happens to work on Mali, is to basically put set event, wait event pairs between every workload, and then the inverse pairs in our post submit stream on the with wait event and set event, and we can stuff some tooling in the middle, and this works brilliantly. So all of our tooling does this. It's probably not going to work on a discrete card, surprisingly enough, but from a layer editor point of view, this is super trivial, right? It's non-invasive to the command buffer recording, other than just adding the events, and we don't have to go and write 10,000 lines of code to manage the splitting. So we do this. It would be nice for debug tools if there was some functionality in the API, which is like, you can do this. Don't do it if you're an application, but I can't believe we're the only vendor who has tooling that does this. And we're all probably reinventing horribly painful solutions. So find out more on GitHub, make your own layers quickly. I think to channel the writing layers is a joy. I'm not going to pretend that's true, but it is at least not now writing 10,000 lines of boilerplate code. We have some off-the-shelf layers. They're designed to diagnose common problems quickly. And so in future, we're going to add more and more support for the data visualization layers that go alongside our other tools, and then you can customize those visualizations. In terms of platform support, currently we mostly test on Android devices because that's our main target market, obviously. It will support Linux because it's not thoroughly tested yet. Adding Lava Pipe for GitHub's on my to-do list. But we do use Linux a lot internally on FPGAs and dev boards, so that will be supported. At some point, I'll look at Windows as well, but that hasn't been tried yet. But it's all on GitHub. give it a go. If you have PRs or requests, let me know. Thank you.
I think it's pretty clear from our presentation that writing layer code is a lot of work, right? And there are certain things you can definitely mess up. Do you have some solutions for testing layer code? Ideally without running the ICD?
No. So the solution we are going to try is use Lavapipe. Maybe have another layer underneath our layer that can output parameters and just check it's making the right modifications to the API. But obviously that's going to constrain the size of example we can run, especially for GitHub Actions. That's the best we have at the moment. Mocking out the entire driver, which is the alternative, is really, really hard. So yeah, no magic, unfortunately.
I guess quick kind of answer to yours. Depending on what your layer does, like a null driver can help sometimes. But again, if you need the actual workload back, then yeah. It's done fun. As someone who's touched a layer once in his life, I will say you've left out a lot of lies, but I'm really glad that this exists. But my question, well, what was the question now? How do you deal with when your code? So if I want this, make a new layer today.
Yep.
Do I grab? Is this something where I would grab, integrate, or how did I go about making a project?
So in the repo, the root directory basically has a common code source tree and then a per layer source tree. You run the script just give it a new directory for your layer. It'll give you a fully self-contained project, and it just sort of includes in the CMake file the stuff in the common directory. And just hit make and run, and you're good. There is some library code in the common directory you can choose to pull in, so kind of standard state trackers and some like useful building blocks, but they're not on by default. So you can choose to pull in some of that. We've got a few ideas there. So like on Android, pushing and pulling files over ADB is a pain. So one of the layers we want to do, just haven't found time yet, is like dump out all the PSOs. You can edit offline and then read them back in again and replay the app. So rather than doing that with local files to the Android file system, which is annoying, we're just going to write a virtual file system over the network. And it's going to look like a file system, but it's actually talking to the host. And you can push and pull files that way. So that'll be some common code that you could then choose to pull in on a per layer basis. But yeah.
So first, again, I'll just say this is awesome. I've heard of somebody who, in their app, they created a layer so that they could use a different driver than was installed on the system. Have you thought about doing that for debug cases?
So the challenge we have is that the OEM customizes the drivers, right? Whether that's functionality, backporting patches, or adding things like display support for the custom display formats or video formats. So we often can't build a compatible driver from ARM when we're not the OEM. So, I mean, you could do it, but it's often not something we have the ability to do.
Yeah, it would be complex. You'd have to call their driver for a lot of things.
Yeah.
But, yeah.
So no, it's not something we've looked at.
Okay.
Khronos loader support? Can you create a layer on, say, desktop for desktop rather than for Android?
Should work. I haven't added all the V2 API entry points. It does work with the Khronos loader on the caveats of hit and hope on some of the things like extension queries.
Okay.
But yeah, should work.
I mean, I can help with that if you would like me to, but
no, I mean, for our Linux dev boards and our FPGAs and the things we use internally, that's on the full Khronos loader. So we need that to work.
Any other questions? In which case, yeah, thanks to our speaker.